We are going to discuss about non-homogeneous recurrence relations. So begin by defining a non-homogeneous recurrence relation with constant coefficients. Then we state the theorem to find the solution to a non-homogeneous recurrence relation. And thereafter we do examples on how to solve non-homogeneous difference equations or recurrence relations. So a linear and homogeneous recurrence relation with constant coefficients is any recurrence relation of this form. So I have an equals to C1 an minus 1 plus C2 an minus 2 plus C3 an minus 3 plus other several terms up to Ck a n minus k, then plus f of n, and we specify that C1, C2, C3, all the way up to Ck are real numbers. And this function, f of n, is a function not identically equals to 0. So these are the kind of equations that we will be interested in solving in this particular subtopic. So when we have an, so let me call this one star. An equals to a1 c1 an minus 1 plus c2 an minus 2 up to plus ck an minus k is called the associated homogeneous recurrence relation with respect to question star. So then we provide a theorem that will help us to say how to write the general solution of equation star. So if an our P is a particular solution of equation star, and ANH is the associated homogeneous solution, then the general solution of star is AN equals to ANH plus ANP. So this simply means the general solution is a sum of homogeneous solution and particular solution. So the key thing is now to find the particular solution. And to find the particular solution, you need to know the structure of f of n. So briefly, let's discuss how to obtain that particular solution. So the solution that satisfies the difference equation or the recurrence relation star with f of n on the right-hand side is called a particular solution. So note that the difference equation and recurrence relation mean the same. So we'll be using either to mean the same thing. So the solution that satisfies the difference equation star with f of n on the right-hand side of the difference equation is called particular solution. And then it should be noted that there's no general procedure for determining the particular solution of a difference equation for any arbitrary function f of n. So however, there's for simpler cases, this solution can be determined by method of inspection. So in simple cases, this solution can be obtained by the method of inspection called trial sequence method. So we provide a few simple cases whereby we can determine the nature of the particular solution when we have f of n. So we have this column will be f of n, and this is trial solution for a n power p, that's simply particular solution. So we can have f of n to be just a constant. So when the right-hand side of star is a constant, then the guess of the particular solution is just another constant. Then f of n can be a power n, where a is a constant, but not a characteristic root. So characteristic root means that it's not among the roots you obtain when you're solving the homogeneous equation. And if this is the case, then the trial solution will be a constant a times this solution a power n, or this constant on the right-hand side a power n. Then we can also have a power n to be f of n, where a is a constant, but one of the characteristic roots. Of multiplicity. Multiplicity simply means the number of times it repeats. Multiplicity m. And if that is the case, then your guess of the particular solution will be a constant a times n power m multiplied by this a power n. We'll demonstrate with a few examples to really understand what this means. Then next, if your f of n is of this form, a naught n power m plus a1 n power m minus 1 plus a2 n power m minus 2 plus all the way plus am, e.g., we can have a naught a power 3 plus a1 n plus a2. That simply means that it's a polynomial in n. Then your guess for the particular solution will be a function of the form a naught n power m plus a1 n power m minus 1 plus all the way plus a power a sub n. And if this is your function, for example, f of n, then you will pick a naught n power 3 plus a1 n squared plus a2 n then plus a3. So these are cubic polynomials, so then you write the cubic polynomial in its general form, even if other terms of the cubic are not in the given f of n. Then if your f of n is a n into a naught n power m plus a1 n power m minus 1 all the way plus am, e.g. we have bn a power m, then your guess for the particular solution will be a power n into a naught n power m plus a1 n power m minus 1 all the way plus am. And if this is our example, then we pick a power n. And this bn is a linear function in n, so you pick a naught n plus a1, which is a general linear function in terms of n. Then next, if your f of n is c power n into a naught n power m plus a1 n power m minus 1 all the way plus am, where c is a characteristic root of multiplicity m, then your guess for the particular solution will be c power n power m into a naught n power m plus a1 n power m minus 1 all the way plus am. And finally, if your f of n is a function of the form an plus bn plus c, where a, b, and c are constants, then your guess for the particular solution will be a function a1 a power n plus a2 b power n plus another constant a3. So we now demonstrate with examples to illustrate how to solve non-homogeneous linear difference equations with constant coefficients. So examples: solve this difference equation. Find all solutions of the recurrence relation an equals to 3 an minus 1 plus 2n. Then what is the solution? when A1 is equals to 3. So when you have a non-homogeneous difference equation, the first thing you need to find is the associated homogeneous solution. So step 1, homogeneous solution, AN. Which means we solve the equation when f of n is taken to be 0, i.e. in our case, we solve an equals to 3 an minus 1. So we let an be r power n be the solution. So this means that an minus 1 will be r raised power n minus 1. So which means that a sub n, we put r power n, 3 r power n minus 1, which means I can divide through by the smallest power of r, which is r power n minus 1. So I have r power n minus 1 equals to 3 r power n minus 1 over r n minus 1, which will be r equals to 3. So therefore, the homogeneous solution is alpha, which is a constant, then 3 raised power n. Remember, we usually write the solution as a constant r power n for the first order homogeneous recurrence relations. So this is the first step to find the homogeneous solutions. Then step 2, find the particular solution. So remember our f of n function is 2n, and 2n is simply a linear function in n. So which means then our guess, if we are to follow what we have been discussing in this previous table, then we'll be taking the form where we have this polynomial structure. So therefore, our guess for the particular solution will be a constant, then plus another constant times n, which is a general structure of writing a linear equation, a linear function in n. So if an is this, then it means that an minus 1 will be a naught plus a1, but the place of n, we will put n minus 1. So which will be a naught plus n a1 minus a1, which are the same as a naught minus a1 and then a1 times n. So then now when we substitute this into the original equation, so we'll have an equal to 3 an minus 1 plus 2n, i.e. where there's an, we put a naught plus a1n equals to 3, where there's an minus 1, we put a naught minus a1, then plus a1n, then plus 2n. So we'll have a naught plus A1n equals to 3 A0 minus A1 plus 3 A1n plus 2n. So which will give us A0 plus A1n equals to, this side constants will be 3 A0 minus 3 A1, then plus coefficients of n will be 2 plus 3 A1 times n. And for us to claim that this equality is a true statement, then this means that constants on either side should be the same, and coefficients of n must also be the same. So from this, we have minus 2A1 equals to 2, which means A1 equals to minus 1. Then now from this other equation, we have, if I take this to the left-hand side, I'll have minus 2A0 equals to minus 3A1, which means 2A0 equals to 3A1, but A1 is minus 1, so it should be 3 times minus 1, which is minus 3. So this means that A0 is minus 3 divided by 2. So therefore now we have the solution for the particular solution, replacing the value of A0 and A1 into what we have said is a structure of the particular solution. So therefore, the particular solution is given by A0, which is minus 3 over 2, plus A1, which is minus 1, times n, just minus 3 over 2, then minus n. And from the theorem on how to present the solution for the non-homogeneous equation, we know that the general solution is given by the homogeneous solution plus the particular solution. So therefore, the general solution an will be alpha 3 power n, then plus this anp, which is minus 3 over 2 minus n. Or we can write an equals to minus n minus 3 over 2 plus alpha 3 raised power n. So this is a general solution of the given problem. So we go to the next example. And the next example is to solve. Example 2, solve the equation, find all the solutions, of the recurrence relation an equals to 5 an minus 1 minus 6 an minus 2, then plus 7 power n. And by in the previous problem, the second part was to what is the solution with a1 equals to 3. So this is the general solution. Just to finish up, this is what we call the general solution. And then the specific solution, we have been told that A1 is 3. So mean that when n is 1, you put 3. The value of the whole expression is 3. So we'll have A1 equals to, where there's n, you put 1 minus 1 minus 3 over 2 plus alpha 3 raised by 1. So which means -1 minus 3 over 2, we get minus 5 over 2. And then remember, this is the same as 3. So 3 is equals to -1 minus 3 over 2, which is minus 5 over 2 plus 3 alpha, which means then 3 alpha equals to 3 plus 5 over 2. Alpha, 3 alpha is equals to 11 over 2. So alpha will be 11 over 2 divided by 3, which will be 11 over 6. So therefore, the specific solution to that given condition is going to be an equals to minus n minus 3 over 2 plus 11 over 6, then 3 raised power n. So remember, when we have been given an extra condition, then we get the specific solution with respect to that condition. And so for this case, the specific solution with a1 equals to 3 is given by this solution. If you are not given this condition, then we will stop at this point. So for this other problem, we don't have another condition given on the recurrence relation. So what we'll obtain will be just the general solution. Step 1, as we did in the previous problem, is to find the homogeneous solution. And homogeneous solution implies you set f of n to 0. So i.e., we solve an equals to 5 an minus 1 minus 6 an minus 2. So to solve this, this is what we call the associated homogeneous equation with respect to this recurrence relation. So let an be r power n be the solution. So we know that an minus 1 will be r raised power n minus 1, and an minus 2 will be r raised power n minus 2. So that this equation will be r power n equals to 5 r power n minus 1 minus 6 r power n minus 2. And when you divide every term by r raised power n minus 2, you'll get r squared equals to 5r minus 6, which will give r squared minus 5r plus 6 equals to 0. So this is what we call the characteristic equation. Now from the characteristic equation, we know that product here is 6, sum is minus 5. So two numbers whose product is 6 and sum minus 5 is minus 3 and minus 2. So I can write this one as r squared minus 3r minus 2r plus 6 equals to 0. So I do the pairing. So this is r into r minus 3 minus 2 into r minus 3 equals to 0. So I'll have r minus 2 times r minus 3 equals to 0. So this means that my r1 is 3 and r2 is 2. So which means then a1 the first value an, which is the general the homogeneous solution will be now a constant, say alpha 1, R1 power n, which will be 3 power n, plus another constant, alpha 2, 2 power n. So where alpha 1 and alpha 2 are real constants. So this is the homogeneous solution. Now, next, we find particular solution. But for particular solution, remember now our f of n is given by 7 raised power n, which is a constant raised power n. So which means according to our particular solution table trial, we let our trial solution for the particular solution to be a constant times this 7 raised power n. Be the particular solution. So we have now to find a n minus 1p, which will just be a 7 n minus 1, and a n minus 2 will be a 7 raised power n minus 2. That simply means that the role of n, when you want to define n minus 1, is taken by n minus 1. The role of n, when you want to define a n minus 2, is defined by n minus 2. So with these values in the original difference equation, which was an equals to 5 an minus 1 minus 6 an minus 2 plus 7n, because we are saying that these are particular solutions, so it means that it satisfies the original non-homogeneous equation. So it means that when I put p here, p here, p here, then still the same function should satisfy that equation. So ANP is a 7 power n, then 5a 7 power n minus 1 minus 6a 7 power n minus 2 plus 7 power n. So then now, I play with this equation to find the value of the constant a. So I'll have a 7 power n equals to 5 a 7 power n times 7 power minus 1, loss of indices, minus 6a 7 power n times 7 power n minus 2 plus 7 power n. So I have a 7 power n equals to, I have 5a 7 power minus 1 minus 6a 7 power minus 2 plus 1. Then I put 7 power n outside. So this equality is only a true statement when coefficients of a 7 raised power n are equal on either side. So a is 7. I remember 7 raised power negative 1 is the same as 1 over 7. So the same as 5 over 7a minus 6a over 7 squared, which is 49, plus 1. So then now I can simplify this equation by multiplying each term by 49. So I'll have 49a equals to 7 times 49 is as 1 over 7 times 49 is 7 times 5 is 35. A minus 6a plus 49. So 35 minus 6 is given by 29. So I'll have 49a equals to 29a plus 49. So 49a minus 29a equals to 49. 49 minus 29 is 20. So 20a equals to 49. So which means A alone is 49/20. So therefore, our particular solution is given by 49/20 times 7 power n. Hence, the general solution, AN, is usually given by the homogeneous solution plus the particular solution, which is the same as AN equals to alpha 1, 3 power n, plus alpha 2, 2 power n, plus 49/20, and then 7 raised power n. So this is our final solution. If you are given the extra conditions, then we'll be able to find the value of these constants, alpha 1 and alpha 2. But because the problem didn't specify any extra information or extra conditions, then we will stop at this as our general solution. Example 3. Solve this equation, AN minus 7 AN minus 1 plus 10 AN minus 2 equals to 3 raised power n. And we have been given extra condition that A0 is 0 and A1 is 1. This is number 3. So you should be able to find first step is the homogeneous solution. So we solve AN minus 7 AN minus 1 plus 10 AN minus 2 equals to 0. This is the associated homogeneous equation. So to solve this, we let AN equals to R power n be the solution. So by doing this, AN minus 1 will be R raised power n minus 1, and AN minus 2 will be R raised power n minus 2. Then we substitute to get R power n minus 7 R power n minus 1 plus 10 R raised power n minus 2 equals to 0. Dividing through by R minus R raised power n minus 2, we get R squared minus 7R plus 10 equals to 0. So here product is 10, sum is minus 7, numbers is minus 2 minus 5. So I'll have R squared minus 2R minus 5R plus 10 equals to 0. So this pair, first pair common is R into R minus 2 minus 5 into R minus 2 equals to 0. So then R minus 5, R minus 2 equals to 0. So R1 will be 2 and R2 is 5. So we know that the general solution when we have this, we'll have AN is alpha 1 R1 power n plus alpha 2 R2 power n. So therefore, our homogeneous solution will be alpha 1 2 raised power n plus alpha 2 5 power n. So step 2 or part 2 is to find the particular solution. Now, remember in this problem, f of n is 3 power n, a constant raised power n. So which means then the particular solution will take the form a constant times 3 raised power n. So by doing that, then an minus 1 will be a 3 raised power n minus 1, and an minus 2 will be a 3 raised power n minus 2. Simply means that to define an minus 1, the role of n is taken by n minus 1. To define an minus 2, the role of n in the assumed solution is n minus 2. So replacing this into the original equation, which was an minus 7, an minus 1, plus 10, an minus 2 equals to 3 power n, we have a 3 raised power n minus 7a 3 raised power n minus 1 plus 10a 3 raised power n minus 2 equals to 3 raised power n. Because when we say that this is a particular solution, then it must satisfy the given original difference equation. So this you write as 3 power n minus 7a. Break this using laws of indices, 3 power n, 3 power minus 1, plus 10a, 3 power n, 3 power minus 2 equals to 3 power n. Then we'll have a minus 7a, 3 power minus 1, plus 10a, 3 power minus 2. Then you factor out 3 power n equals to 3 power n. So you will get, this implies that a minus 7 over 3a plus 10a, 3 squared is 9, should give us 1, coefficient of 3 power n on the right-hand side. So here we have 1 minus 7 over 3 plus 10 over 9, which will give us negative 2 over 9. So negative 2 over 9a equals to 1, which means a alone is minus 9 over 2. So therefore, the particular solution is given by minus 9 over 2 times 3 raised power n. So the general solution is given by the sum of the homogeneous solution and the particular solution, which means an is going to be alpha 1 2 power n plus alpha 2 5 power n minus 9 over 2 times 3 raised power n. So then now we were given that a0 is 0 and a1 is 1. So where there's n put 0, so we'll have alpha 1 2 power 0 plus alpha 2 5 power 0 minus 9 over 2 3 power 0 should give us 0. And then alpha 1 2 power 1 plus alpha 2 5 power 1 minus 9 over 2 3 power 1 should give us 1. So we'll have, from this first line, we'll have alpha 1 plus alpha 2 minus 9 over 2 equals to 0, i.e. alpha 1 plus alpha 2 equals to 9 over 2. Then the second one will have 2 alpha 1 plus 5 alpha 2 minus, so 9 by 3 is 27 over 2 equals to 1, i.e. 2 alpha 1 plus 5 alpha 2 equals to 1 plus 27 over 2, which will be 29 over 2. So if I multiply the first equation by 2, I'll get 2 alpha 1 plus 2 alpha 2 equals to 9. And the second equation is 2 alpha 1 plus 5 alpha 2 equals to 29 over 2. So then I can now subtract these two equations. So 5 alpha 2 minus 2 alpha 2 is 3 alpha 2. And then 29 over 2 minus 9, I get 11 over 2. Then to get alpha 2, I divide 11 over 2 by 3. That will give me 11 over 6. So alpha 2 is going to be 11 over 6. So from equation 1, alpha 1 is the same as 9 over 2 minus alpha 2, which is be now 11 over 6. So that will give me 9 over 2 minus 11 over 6, which will give me 8 over 3. So this will be 8 over 3. So therefore now with those two values of the constants, alpha 1 and alpha 2, now we have therefore the specific solution is now an equals to 8 over 3, then 2 power n plus 11 over 6, then 5 power n plus minus 9 over 2, and then 3 power n. So this is what we obtain for that particular problem. So at your own free time, try to solve this. Solve the difference equation. An plus 6 an minus 1 plus 9 an minus 2 equals to 3, with a naught equals to 0 and a1 equals to 1. So know that now in this case, when you'll be finding the particular solution, your f of n is given by 3, which is a constant. So when you'll be finding your particular solution, then you'll assume that the particular solution is just another constant a. And when you solve this correctly, you'll find that the solution is negative 3 over 16 minus and then minus 3 raised power n plus 3 over 16. So this is a solution to that particular problem. And then the other one is an minus 2 an minus 1 equals to 5 times 2 power n, where a naught is given by 7. So when you work out, you will find out that the solution here, you'll get an equals to 7 2 power n plus 5n 2 raised power n. And because, just to make things clearer, because f of n is given by 5, then 2 power n, which is a constant, times 2 power n, then your particular solution will be given by a constant n 2 power n, since when you solve for the homogeneous solution, you get that your homogeneous solution is going to be a constant 2 power n. I remember when the constant 2 power n is appearing in f of n, then to get particular solution, which should be a linearly independent solution to the homogeneous solution, you must multiply the whole expression of a constant a power n by another n. If you remember in the definition we gave in this table, when you are writing the general structures of the particular solution, we say that when a power n is what is your f of n, and this a is part of the characteristic root, then the solution you pick as your particular solution, you must include an n raised power m, the multiplicity of that root a, to ensure that the particular solution is actually linearly independent with respect to the homogeneous solution. But if you get a case whereby the f of n is not having a constant that is exactly the same as what we have in the form of the homogeneous solution, then you don't put this n at this point here. So do more practice on the same kind of equations. And in case you have any problem, feel free to contact me. Thank you.